Hey students, in this video we're going to talk about double integrals. So first, I open an applet in GeoGebra. All right, so what a double integral is just the volume of a region, in this case on a rectangular region. So like I've already put the first example in, and what we're doing is just finding the volume that we get if we integrate from 0 to 1 for x, and then from 1 to 2 for y. So in single variable calculus, we learned that the definite integral represented the area from one point to another. So it makes sense that if I take an area and then I integrate it, I should get a volume because I'm adding depth to the area. So the process for doing this is very straightforward. You integrate from the inside out. So whatever integral is entered with its differential, that's going to indicate the variable that you should integrate first. So here, this would indicate that we need to integrate y first, and then whatever we get, we integrate the next integral with respect to x, and that's it. Now again, all of the same rules for integration apply. Use substitution, integration by parts. If we have it, partial fraction decomposition. All those things are in play here. So let's get started. So for our first example, again, we already see that region. It was in GeoGebra. Um, what we get here again is going to be a volume, a three-dimensional quantity. So if we're considering that we integrate x first, now the way I would do this is just say we're separately working the integrals. So the integral from 0 to 1, and if we're integrating x, the y, we can treat it like a constant. So it's just going to be y times this integral from 0 to 1 of 4x dx, which we know is going to be y, and then the antiderivative of 4x is 2x squared. So, well, actually, let's go. So it would be 4x squared over 2 evaluated from 0 to 1. And that's actually what we know to be, we'll say y times 2x squared from 0 to 1. And now we apply the fundamental theorem of calculus, which means we substitute in 1, subtract what we get when we substitute in 0. So we're going to have y times 2 times 1 squared minus 2 times 0 squared, which is just 2y. So now we need to integrate 2y. So we're going to integrate from 0 to 2 of the function 2y dy, and that's just going to give us y squared from 0 to 2, which is going to be 2 squared minus 0 squared, which equals 4. So what that would mean is that the volume of that region that we saw over in GeoGebra is 4. So that's it. So I got tons of examples in this PDF. We won't do all of them. Now you can work them independently, but some of them are just to like reinforce this concept. But to demonstrate the concept, we don't need to do all of them. So we're going to skip example 2 and move on to let's do this one. So we'll do example 3. So what we need to do is convert this implied region R into a double integral. So uh, so let's see. So if we're integrating from 0 to 3 for x and 1 to 4 for y, what that means is that we would have a rectangular region. Who knows how the function looks above it? We could graph it, but we're not very interested in seeing the graph. So then 1, 2, 3, 4. So what we're doing is integrating a region that would be like bounded on that interval, x squared plus xy, and it would just have like it would have some height above or below the xy plane, but we're integrating over this region. So sometimes it doesn't matter the order in which you integrate, and sometimes it does. Now we'll see in this example, because these are polynomials, it won't matter the order that we integrate. Neither direction is going to be harder. So this is, we'll say we integrate x last. So we'll put the x on this on the outside. I don't know what just happened here. So we'll integrate from 0 to 3 for the x, and then we'll integrate from 1 to 4 for y. So then we have x squared plus xy, and we'll have dy and dx. So this is the integral from, I'm doing this a different way than we did in example 1. So this is the integral from 0 to 3. If we integrate the internal integral, that would give us, for y, that's going to be, so x squared is a constant, which means we add a y to it. So that would give us x squared y plus, and then if we integrate y, we want to get y squared over 2. So that's going to be x y squared over 2, and we'll evaluate that from 1 to 4 dx. So now if we want to actually do this calculation, so what we're doing is uh, x squared times 4 plus x times 16 over 2 is 8. And then from that, we're subtracting what we get when we substitute in 1, which is going to be x squared times 1 plus x times 1 squared over 2. So just really 1/2 x. And that's going to be 4x squared plus 8x minus x squared minus 1/2 x. And that equals 3x squared. 8 is 16 halves, so minus plus 15 halves x. So we have this new integral from 0 to 3 of 3x squared plus 15 halves x dx. Let me check my math because I work quickly sometimes. 4 times x squared is 4x squared, 8x, and then minus x squared, 16 over, yeah, all right, we're fine. So if we integrate this, we're going to get the antiderivative of 3x squared is x cubed. And then we're going to get plus 15x squared over 4, evaluated from 0 to 3. We don't even have to worry about the 0 because it's going to produce a 0. So we're going to get 3 cubed plus 15 times 9 over 4, which is 27, plus 9 times 15 is what, 135? Yeah, plus 135 over 4. And 27 over 4 is the same as, I believe, 108 over 4. So that's 108 over 4 plus 135 over 4, which is 243 over 4, or 60.75. No, conveniently, we can actually check this in Desmos. So let me pull up the Desmos. Um, let's clear this all out. And we can actually just do a double integral. I'll actually show you how we can do this. Calculus. So we want, it was from 0 to 3 for x. And I think and then we had, was it 1 to 4 for y? 1 to 4 for y. And it was, I forgot the function already, x squared plus xy. So, oh, wrong thing. X, oh, x squared plus xy. And then we have to add our differentials. So we're going to have, it was dy dx, so then dy dx. And you see that we get that 60.75. It just spits out the number for you. So it's a handy way to check this stuff because sometimes the integrals are slightly more difficult. And as a fraction, it was 243 over 4. So, cool. All right, we'll need to do example 4. All right, so example five. Um, when we're choosing the best order to integrate, sometimes one variable is preferable over the other. And the reason being is that one way could force you to have to do something like integration by parts or partial fraction decomposition, where if you swap the variables, it won't matter. So, like, imagine we try to integrate. I can't even remember. We'll see which order turns out best. We don't care about the limits yet. So let's say we had some double integral, and it was negative y. It is negative y sine xy, and we tried to do dy dx. Now the problem here is that y sine y doesn't have an easy antiderivative. This requires integration by parts. But if we switch this around, where x is the variable integrated first, like maybe we could use like some simple u substitution that makes it work out easier. So let's do that. So we want to say we integrate x first. So that means our y limits on the outside. So from 0 to pi over 6, and then from 0 to 1 of negative y sine xy. So, and then we're going to have dx dy. So if we do a u substitution, we're going to let u equal, all right, so we're doing a substitution so we can just integrate sine. So u is going to equal xy, and the derivative of xy with respect to x is just y, dx. And so you know how u sub goes. We would have du over y is equal to dx. So we can, oh, and also if our uh, x limits are from 0 to 1, our u limits are going to be from 0 to y. Because you remember, you take these values and you substitute them in here. So now our inner integral is from 0 to y, and we have uh, negative y sine xy is replaced by u, and dx is replaced by du over y. So du over y. So now notice the negative y and the y cancel, and what we have to integrate is just from 0 to y of negative sine u du. And conveniently, that just turns into cosine of u, and we need to evaluate that from 0 to y. So that's going to be cosine y minus cosine 0, which is just the cosine of y minus 1. So now our outer integral, we integrate from 0 to pi over 6, and that's just cosine y minus 1 dy, which is sine y minus y evaluated from 0 to pi over 6, and that's going to be the sine of pi over 6 minus pi over 6, and then minus the sine of 0 minus 0. Both of those are actually 0. And so this is 1/2 minus pi over 6, which I think is going to be a negative value because pi is 3.14, so it should be negative. We'll see. Maybe it's like slightly positive. I actually have no idea. So let's throw this into Desmos as well. So let's change our limits. It was from 0 to pi over 6, I think, for the outer limit. So it's from 0 to pi over 6. Also, if you're going to use Desmos, make sure you are in radians. So from 0 to pi over 6, and the other one was from 0 to 1, and the function was, it was dx dy. So we're going to say dx dy, and we need to actually change this to be negative y, was it sine? Yeah, negative y sine xy. Yeah, so it's the volume is slightly negative because if we did 1/2 minus pi over 6, it gives us that value. So it's slightly negative. All that means is that the volume is just below the xy plane. Doesn't really matter. The absolute value of it would still be a positive value. So, all right, the last thing is average value. So, the way to think about average value is that it's like the average rate of accumulation per unit increase in some quantity. So, when we're accumulating volume over this rectangular region, if we divide by the area, that's how much we're accumulating per step. Um, and so right now we're dealing with a rectangular region. So the average value is just 1 over the area times the volume that we get. And again, for a rectangular region, that's just length times width. So here, for example 6, our area is, all right, so from 0 to pi is pi units long, and from 0 to pi, again, is pi units long. But for the sake of argument, say this was like 1 instead. So then this interval is, one side is pi minus 1 units long, the other interval would be pi. You just subtract the two endpoints, and that's the length of that side of the rectangle. So here our area is pi times pi, which is, of course, just pi squared. And we want to find the average value of this function sine x, sine y over this region. So it doesn't matter which way we integrate, it's the exact same integral. So from 0 to pi of sine x, sine y, and we'll say we integrate y first. So the inner integral all right, so sine x is a constant, so sine x, and then we're integrating sine y dy is negative, so we're going to have actually sine x, and then multiply by the antiderivative of sine y, which is negative cosine y, and we need to evaluate that from 0 to pi, so we're going to let this sine x just hang out, so negative cosine of pi minus, and so this is the key part when we're doing the fundamental theorem, is minus negative cosine 0. And so this is going to be sine x. So the cosine of pi is negative 1, and the cosine of 0 is 1. So that's 1 plus 1, which is 2. So we end up with 2 sine x. So now we need to integrate from 0 to pi of 2 sine x dx, and that's going to be negative 2 cosine x evaluated from 0 to pi, which is negative 2 cosine pi minus negative 2 cosine 0, which is, again, the cosine of pi is negative 1, so we're going to get 2 plus 2, which equals 4. So the average value is 1 over pi squared times our volume, which is 4, which is just 4 over pi squared. So what that would mean is that, so once you've integrated from 0 to pi, we'll say in like the y direction, what the average value is going to mean is, well, we would just be integrated, we would be adding an amount of 4 over pi squared along the interval along the interval from 0 to pi. Each time we'll be adding just that amount to our volume until we've covered the whole thing. All right, so The rest of these problems are just different examples of integration. I do recommend you look at them at least, and if you have questions, talk to me in class, but they're just bunches of integration. But the process for solving a double integral: choose a variable to integrate first, apply the fundamental theorem, integrate again, and apply the fundamental theorem. Sometimes the order in which we integrate does matter. See y'all in class.